Good morning. How you guys doing? Feeling all right with the storm coming? This first time for some of you? Some of you not, probably. Well, thankfully it looks like it will not be too strong as far as hurricanes go, but quite wet, I think, so be prepared. Got the boots and everything already, I see. I wore my hiking boots, which are relatively waterproof, not quite as protected, but yeah. At some point, you just give up all hope, right? Just the sandals. Yeah. So if you haven't been through a hurricane, I think that the worst that is going to happen is some people will be out of power for a while, and there will be some flooding. So what I encourage you all to do, you probably already know this and everything, but keep in mind, if you have a car, try not to park it in a low area near a storm drain or something like that. If you find a spot where you can park with a little more elevation without a tree that's threatening to fall over on it, those are good things to think about. As far as your personal safety, of course, be careful if there are flood waters, especially driving. You probably aren't likely to gonna go try to swim while the hurricane is in session, but obviously. And don't go too crazy with trying to prepare food-wise. You don't have to empty the grocery store, but make sure you have a thought of what do you do if you're a day or so without food or water. Do you have something you can rely on is a good idea. I think after a day or so, we should probably have a lot of people coming back to power or be able to access places. So it's good to be prepared, but don't psych yourself out. Okay, how do you guys think about the MATLAB homework? Hard? Okay. So I didn't go through it all myself, but I think maybe now I should. What was hard about it?
It required you to remember a lot of stuff and then put all the pieces together at once.
Okay.
And it was.
So you had to go backwards sometimes and like, oh wait, what was this?
I don't think you could go backwards. At least
Oh.
I was just like doing it, and I was like, I remember it was something like this. So I was doing like,
Okay, interesting. So it was like, it put you in like a quiz environment where you couldn't do that?
no,
But
they don't give you the answer. You can request the
solution.
okay. So there's an easier way that
So it was easy to make 100, but to do it on your own, like after about half of it, I started forgetting what
right.
was.
I think there's too many new things.
Yeah. That makes sense. Yeah, and it's hard to think that you're gonna master it all in 2 hours like that and be able to do it. Like for me, it's probably like if I spent an hour on it and just sped through a few things, that probably refresh enough my memory, it'd be like exactly right. And then I'd forget a couple things and then spend an extra half hour remembering. But yeah, that makes sense. Like if you've never seen it, but do you feel like you can do something in MATLAB now that you've done it? Okay, so that sounds like a pretty big win in my book. Okay, I've not prepared any MATLAB to do today, so apologize. I'm a little behind on some things, so I didn't quite get there. Regarding class Thursday, we just got an email saying classes are going to be online. I'm all right with that, and I should be able to prepare for that, no problem. You know that I do the streaming thing anyway, so that should be possible, assuming I have power and internet, and assuming I have power and internet tomorrow to prepare the lecture. So I will plan to do so. It'll be on our YouTube page. There is a link now on the syllabus or in the Moodle, or there should be. It's also on the syllabus. It's if you just go to youtube.com/@snowslab. That's the handle. So you should be able to see it there. And if you're there live, essentially what you can do is, let me drag this screen over for you. You'll be able to chat. In fact, if somebody, maybe I ought to do it right now. you'll be able to chat. I'll see it show up right here. In fact, there's been a couple people spamming or just hopping in here and there. And I'll see it there. And then if somebody else, your classmates here, you'll also see it there. So if you're like, have a question, you can ask it on the YouTube channel itself, and it'll show up to me there, and I'll be able to answer it. And there's probably a 10-second delay or something. So it's not going to be like completely immediate, but it will be fairly quick. So I'll just load up YouTube so you can see that. Yeah. So let me, I'll bring up my channel so you can see what it looks like to, I'm logged in as myself right now, so I'm not sure how the chat's going to work, but you see the small delay there. And if you were logged in with somebody else, or maybe I can do it here. You see the small delay there. You can chat, yeah. So put it there, and it also pops up on my window. I'll show you. Put it there, and it also pops up on my window. Keep grabbing the screen. I'll show you. Put it there. You can see it showed up here. It's cutting it off a little bit. So I'll be able to see it here and talk back to you and all that. So it's not quite like Zoom, although if you want to, you're welcome to say, hey, can you hop on Zoom and let's talk this out? And I can do that. That's no problem. But this way, there's not all the beeping in and out, and it's just automatically recorded and up there. And to me, it's just a little more convenient. And hopefully that's convenient for you. You don't have to think about, what are you wearing? Have you brushed your hair today? Whatever, you know. It's anonymous that way. And I think that works a little better, especially for my bigger class. For you guys, I'm kind of partly tempted to say, well, let's just get on Zoom, but I don't have my PowerPoint set up for that and everything. So that's my plan. So if you want to adapt or whatever, that's fine. And I also know you guys might not have power, right? There's also that chance, right? So what I'll say is expect me to provide a lecture there and be able to engage with me as best you can, or to, add a comment or email or whatever and get more engagement. But if I'm not showing up within the first 10 or 15 minutes and you haven't heard any emails from me, probably no lecture. We'll just cancel. So I think LSU's doing something interesting here by assuming that classes will be in place. Like I'm kind of ready and willing and everything, but I don't know. They seem a little ambitious to me. Okay. Any questions or concerns about that? All right. So that's the plan. All right. Last time we left off talking about chemical potential. Still have a few things to talk about there. We were using it to kind of come to this Gibbs free energy concept. And I realized it'd probably be a good thing to take a step back and look at the very fundamentals of Gibbs free energy. And so I'm bringing in some content from a nice online resource, the Khan Academy. You've probably seen it before. So we'll take a look at some of the basics from there, and even watch a video that it's just somebody solving a problem. And I think it gives a good expression of, hey, here's how you do this stuff, to make it practical to solve a problem for a simple chemical reaction. Stuff you've done before in Gen Chem, I'm pretty sure. But just to lay it all out there and have that. So I'm going to spend a couple moments reminding us where we left off, and then hop into that kind of a bigger picture overview. Then we'll get back into specifics of like, really, what is this chemical potential? How does that relate to this Gibbs free energy, so that we can be a little more detailed with our analyses and understanding how different equilibrium are coming to be, and the different things that affect that. So that's today, and I do have a couple practice problems along the way, including the one that the video will solve. Okay, last time we left off, we were talking about how chemical potential can be zero, can be positive, can be negative. So a given chemical in a particular situation can have potential to have a reaction or to exert some energy. So we thought of this as you could put a ball or some object on a top of a skyscraper, and relative to the ground level, that has some potential energy. You could also dig a hole and put it way beneath, and that has sort of a negative potential energy as compared to the reference state. So it's kind of a reference state potential energy. The same scenario as with chemical potential, can be at the ground state, whatever we define that as, can be above or below. Mostly we're interested in that difference. Okay, so we describe then a standard state of chemical potential that is convenient to our daily life, which is room temperature at 1 atmosphere. So room temperature at sea level, basically. At that point, we say, we also describe that as the activity equaling 1, meaning if you have an activity coefficient, you're including that, and you have 1 mole, I guess molal, of that substance. So in dilute aqueous systems, 1 moles per liter of the stuff at standard conditions, that's your, with no other things affecting your activity, that's the standard default state. So lots of elaboration there now that we've touched on each piece of that. So now we have a pretty good understanding of what's going on with this definition. We also said R is that universal gas constant and T is temperature in Kelvin. Okay, so with that, we can then begin to piece together what kind of reaction, what kind of energies are influencing a given reaction. That's the whole point of calculating the delta G. We also mentioned the gas constant, universal gas constant. This also has to do with that embodied energy, this gas constant times temperature. That's part of what we say about that pressure times temperature or pressure times volume work stuff and all those assumptions we had to make. All right, let's see. Just check one thing. Good. Okay. So, a couple more details on the more theoretical level, and then we'll take the step back out to the bigger picture. So when we want to apply the chemical potential in some way, we're really trying to find a way to get to Gibbs free energy, to relate that potential energy of a chemical to the wider picture of what we call Gibbs free energy, that describes the total energy available in that system. And specifically, we're interested in the change in Gibbs free energy because that will tell us, is this a spontaneous reaction or which direction it's going to go, or have we reached equilibrium? So that's the bigger picture. We'll take a step back out and really make sure we're clear on all of that and the how and why of what delta G means. But since we're in the weeds, let's continue a moment longer. We're looking at an equation here saying the delta G is going to be the sum of all delta G's for each species, which we can define as N times the U, so the moles times the potential energy of the moles. And when we have the delta, we're talking about before and after some given reaction. So we have an initial condition and a final condition. So we're doing final minus initial, essentially. So if we have multiple species of chemicals, some of them might have a high energy at the initial condition and a low energy in the starting, or it could be reversed, right? So whatever is happening, we're going to see that chemical potential show up here and inform our before and after for the delta G. And we need an equation that really accounts for everything in there because we're summing from every species here. Okay, so we can rewrite that if we recognize that, if we take a look at a couple things, we can rewrite this a bit to say this is the sum of the final moles of each species times the standard state plus this RT natural log of its activity. That's going to be the final condition. And the initial condition would be a sum, likewise, of this N times that standard state plus RT natural log of the initial activity. So it's final versus initial activity there. So we're just expanding that to say, well, this thing can be described as this. So the that chemical potential we can expand to say the chemical potential is the reference potential plus the current potential, right? So if this is the reference term, then this is more like a current term, right? So or actual, or whatever, however you want us to describe it, right? So it's like the reference is ground level, and this is some height above ground level. That's the dynamic. And this, we're checking this for both before and after. So we do some reaction, and maybe we push the ball up higher up the skyscraper. We take an elevator up, right? Now we can compare the initial, which had some maybe difference from reference, to the final, which has a different difference from reference. That's what we're saying. Okay, another component here is we can recognize, since we have a summation over all of the species here, we actually have some ways to handle all species in a reaction. And if you recall, when we described an equilibrium constant, we set it up as the products over reactants based on the stoichiometry. So I'm going to skip a little bit of derivation that the book's going through. Essentially what it's saying is we can incorporate the stoichiometric coefficients for this type of reaction, right? These stoichiometric coefficients, we'll say these are VI. Okay, and all this is saying is when we describe with stoichiometry, we can set it up to account for all of that. And since we do typically products minus reactants or products over reactants, depending on how we're arranging things, we can describe that stoichiometric coefficient for each of them and put that in terms of NA, NB, NC, and D. And we're going to end up with a minus in some particular cases based on the way we define that system. So that's the derivation that's happening here. You're welcome to go take a closer look about all that. With that, we can then say our delta G is going to be the sum of this guy. Instead of using just a generic N, we're going to use the stoichiometric here, okay? And then include that over here. This will be the same, it'll be the same deal because the reaction, it's not so important about how much we have, it's actually more of the ratio that we have. Because what we're going to do is react a certain number of moles of this with a ratio, certain number of moles of that, right? There's going to be a ratio of that reaction. So that's where we're heading with this particular derivation. Okay, so from there, which is copied again right here, we can elaborate a little further or take a little side note maybe and say, well, the standard Gibbs free energy, this Gibbs free energy not, we can define as just this portion because we're just at the reference state, right? So this will be the reference position, so to speak. So that would be this guy. And we can write that as that V times delta G of formation at standard state. So with all of that, we're basically saying, we're basically connecting the concepts so that we can rewrite this term here with the delta G naught. So this is the formulation we've seen quite often. Delta G equals delta G naught plus RT natural log of something. Now that something, the Q here, is where a little bit of magic happens with the products over reactants stuff. This Q is a quotient. So here we would have the activity of C to the C power times the activity of D to the D power divided by the activity of A to the A and the activity of B to the B. So this is very much like when we said, oh, we're going to have C to the C power times D, you know, in a dilute aqueous system where you can use just concentration. In being very particular about it and correct about it, we're using activity here. So that's what's happening. And that would be over the reactants. Okay, so we've seen that before. We kind of understand where that's coming from, and we can write it with this kind of product notation. But essentially, that's the Q here, right? So this gives us a way to combine all of the different species into one equation and say, here's where we're at. That's kind of the point here. Does that make sense? So I'm skipping a little bit of that derivation, but it's just simply getting that quotient into place correctly, and then we can write it a little more generally here. Okay. So from there, we can make a couple more observations. First of all, if every activity is 1, which is where we're at if we're at the standard state, then that's perhaps how we should define the standard state, right? So in that case, delta G is equal to delta G naught, because if we take a look at, well, I kind of by definition, but delta G would be equal to delta G naught. That's just this side of the term. So how do you get there? Well, the natural log on the right side, you ask yourself when you solve with natural log, okay, e to the power of what equals this number, right? So in order to get that whole term to go to 0, that term will go to 0 when the Q is 1, right? So when Q equals 1, the answer is ln of Q equals 0, because 10 to the 0 equals 1, just like e to the 0 equals 1, right? Anything to the 0 power equals 1. So as soon as that Q gets to 1, that whole term goes to 0. Let's see, so I probably should write that here. So that term goes to 0, so therefore we get this value. So it's just a kind of a fancy way to say when all the chemicals in the species are considered at standard state, then that's the delta G. Yeah. Okay. So another thing we can say is a system at 25 Celsius, 1 atm, when a system at standard temperature and pressure is at equilibrium because delta G equals 0, then we know something else. We know that the Q is equal to the K, that coefficient, the equilibrium coefficient, right? So when we said K is essentially this stuff, well, when that is true, when the K is equal to Q at these conditions, then we've reached equilibrium. Let me see if I said that right. When a system is at standard temperature and pressure, when it is at equilibrium because delta G equals 0, then Q equals K. Okay. So if we get delta G to equal 0, that also says we're at equilibrium. All right. So when we write it that way, putting this to 0, this is the equilibrium. This is one of those concepts we're going to take the step backwards and take a big picture look, but this is one of the definitions. When the delta G is 0, that means essentially we don't have any difference before and after some given reaction. It's going to be the same amount of energy, you know, regardless. So that's kind of, by definition, that means we're not out of balance. We're not pushing one way or the other with the equilibrium reaction. So if we have that definition, then that delta G drops out, and we can then define what delta G naught is in terms of the K for our equilibrium constant. So we can have this expression where delta G naught is equal to minus RT, natural log of that equilibrium constant. That gives us a way to define K in terms of delta G naught, which is very useful because delta G naught we can know just from standard reference state lookup table stuff, right? If we know the standard state of some particular chemical under those standard conditions, and we know that for each one of the chemicals in the situation, then we can know K, which is quite handy, assuming we know the temperature and we get the right rate, the R constant. So that's to say delta G naught is equal to minus RT natural log of K. Now we can transform the natural log into a regular log. That's the only thing that's happening here from this guy to this guy. So ln to log. That's a transformation, and that's the number that, the factor that we can pull out that transforms it. Okay, and I guess that's probably, is that 2.303 times E is equal to 10 maybe? I don't remember exactly how the math works out, but something like that. Okay, so we have that expression. We've probably seen that one a lot. And ultimately we can see that our delta G is delta G naught plus RT ln of Q. Okay, another way we could say it then, given this and given this guy, I'm sorry, this part I just pulled back because that's what happened. So this is the equation that the book was calling back to. So given this that we already talked about, and this one that we just derived, we could also describe delta G here as 2.303 times RT times the log of Q over K. Now the log of Q over K is kind of interesting, because this is where instead of taking them, one plus the other, because this would look like negative 2.303 RT log K plus RT ln of Q. If we write this guy out, substituting this to here, that's what we get. And we can combine logs if we have the same terms, so we can combine we can do some factoring out, right? And the log K plus the natural log Q, but we transform it into, instead of natural log, we transform it into a normal log. We do a little bit of algebra, and then we get this guy here. Okay, so that's how we end up deriving this final equation here. Delta G is 2.303 RT log of Q over K. And when you stop and think about it, Q over K, that's the Q being the current activity quotient. So whatever the system is at this moment with different activities, maybe we're nowhere near equilibrium, it's going to be some value. Or nowhere near equilibrium, or maybe equilibrium, but nowhere near standard state is what I should have said. But K is when we are at standard state. And so the difference between where we're at with reference to standard state and if we were at standard state, that information is contained there. That's why we can account for both the delta G naught, which is a reference, because K is accounting for that reference. So K is sort of acting as a reference. Well, really this whole equation here, the delta G naught, right? So this whole thing, but especially that's where the information is contained. But this way we have an equation that accounts for the current situation compared to the reference. That's the point. Okay, and it just so happens we have a division now because of the log properties. And the way we rearrange this, I think we would probably say RT ln of, this whole thing is equal to, so delta G, we can rewrite it to just move those, right? RT ln Q minus 2.303 RT log K, excuse me. We can just rearrange those, and that's why we'll get Q over K. When we do the subtraction, that means in the natural log, when we combine, or the log, when we combine two, it's dividing by instead of subtracting. That's the log rule. Does that make sense? Clear enough on that? Okay, so all of this is really giving us a firm foundation of where this stuff is coming from. But at about this point, I was like, you know what? I think at least I need to take a step back and remind myself, like, what are we doing with the delta G and everything? And so I guess the book is assuming too much of us, or at least me. All right, so here, the link at the bottom here, this is the Khan Academy article, and there's a video that follows it, so we'll go in that, watch that in a couple minutes. So what exactly are we indicating? In practical terms, what is the review of this? And we touched on the second law of thermodynamics already, but I really want to be clear, what is delta G doing and what is it telling us? So, second law of thermodynamics, the universe is becoming, it's increasing in entropy, right? And the sort of the relationship between entropy and enthalpy is described as, we can say this Gibbs free energy term is equal to the enthalpy minus the entropy. So H being enthalpy and S being entropy. So that's kind of the general form, right? So we've already talked a little bit about this. Delta G we can define as that enthalpy term and then a temperature times entropy. And you'll see this is a very, very parallel to these terms, right? So it's very, very much related, and that's where we are going to go with all of this. And we can also say that since we're interested typically in changes, we'll just write a delta in front of all of that and just consider the change in each of them to do our calculations. Of course, we typically are going to want to keep the temperature constant to make that more convenient, although we could keep other stuff constant and see what happens if we change temperature, I suppose. But let's not go there right now. So we have a kind of a generic equation here, and we understand we were deriving all this stuff based on the fundamental activity and all that. But kind of at a higher level, at constant temperature and pressure, that change of Gibbs free energy is that change in enthalpy minus the change in entropy. When we have a negative delta G, that means we are spontaneously going forward. It's exergonic. It's going to happen given a particular temperature, if that's the case. Okay, so what it lets us do then is kind of delta G we can think of as the energy after the reaction compared to what we had before the reaction. So if we have the energy after the reaction minus what we have before, and we've released energy, that number becomes negative. That means it's going to be likely to happen. Right? That's telling us it's spontaneous. If delta G is 0, we said earlier that's equilibrium because the energy didn't change after the thing happened. We swapped some things around and nothing changed. Right? So that's completely at equilibrium. When delta G is greater than 0, we would call that endergonic and not spontaneous in the forward direction. Instead, it will spontaneously go backwards if the system allows that to produce more starting materials. Of course, sometimes we don't have an equilibrium reaction. We might have something that could only go through in a forward reaction, so we're not going to spontaneously create methane out of CO2 under normal conditions, but we might spontaneously, it could go the other way. So certain times it's just doesn't necessarily make sense to go backwards, but then again, maybe that's just all about the delta G. Okay, so that's kind of the big picture is the energy comparison before and after some given reaction, right? That's what the G is telling us, or the delta G rather. And we can, again, look at that as a final minus initial sort of a situation. Okay, so when is delta G negative? If we take a look at our equation here, we have a nice little box that's kind of considering these two terms to say, well, both of these terms can be positive or negative, and they can have different magnitudes. So at what point do we have the negative G values telling us that it's going to move forward? So there's only really 4 options we can look at on the first cell here. Let's look at the first column. We have 2 conditions where the change in enthalpy is less than 0. So this term is negative. So whatever happens to the enthalpy is negative. Well, now we can say, given that we're going to assume that's negative for 2 conditions, what about this guy? At what conditions of that are we going to have a spontaneous reaction? So if the change in entropy is positive, then we will always have a spontaneous reaction at all temperatures, because we have a negative minus a positive, right? So a negative minus a positive, then always negative, right? It doesn't matter how positive this is, doesn't matter the temperature here, and temperature is going to be on an absolute scale, the Kelvin scale. So that's always going to be, no matter the temperature, even if we took temperature to 0, so this whole thing goes to 0, it's still going to be negative, right? That's what we're saying. Okay, so let's consider another case. If this guy is less than 0, so now we have a negative minus some other negative. Well, that could be positive or it could be negative, right? Depends on the magnitude. So this one's going to be spontaneous so long as temperature is pretty low. So if we have a negative, minus a negative is typically we're adding, right? So we're adding some value to this first negative. Well, that's going to be, if the second term is small enough, we're going to stay in a negative spot. So so we're going to have a spontaneous reaction at low temperatures when that second term is small enough to not overwhelm that first. Does that make sense? And this is why we could have some conditions where we might actually have to lower the temperature to have a reaction go forward. I don't think those are very common situations, but it's certainly possible. And it's probably something we all did in Gen Chem. All right. So let's take a look then when delta H is positive. So when we start with a positive here. How does that work? Well, it's the same type of deal. We're just basically inverting it. So if we have a positive minus something else that's positive, it's going to depend on how positive that second one is, right? That's just where it's at. So then again, it depends on the temperature. And likewise, if we have a positive minus a negative, that is like adding more to it. So it's never ever going to be resulting in a negative number. So in that case, in that last box there at the bottom right, it's never going to be spontaneous. Okay, so that gives us a framework then to maybe still not very intuitive. Okay, well, what is entropy? What is enthalpy? But we can see that particular conditions are going to favor or disfavor spontaneous reactions. And we also see how it depends on temperature, right? Sometimes you just don't have something happening until you heat it up, right? Or it happens very slowly until you reach some temperature threshold. So that's kind of a explanation there. All right, I'm going to come back to this in a second and watch this video. Oops. Now I should probably adjust my sound and stuff too. Oops. So just a moment. All right, going to test that. There we go. Okay. All right. And
have this reaction here where if I had a mole of methane and I react that with 2 moles of oxygen, I'll produce a mole of carbon dioxide and 2 moles of water. What we want to answer in this video is whether this reaction is spontaneous. And we learned in the last video that to answer that question, we have to turn to Gibbs free energy, or the change in Gibbs free energy. And the change in Gibbs free energy is equal to the enthalpy change for the reaction minus the temperature at which it is occurring times the change in entropy. And if this is less than 0, then it's a spontaneous reaction. Spontaneous. So I gave us a little bit of a head start. I just calculated the change in enthalpy for this reaction, and that's right here. And we know how to do that. We've done that several videos ago. You could just look up the heats of formation of each of these products. For water, you'll multiply it by 2 since you have 2 moles of it. And so you have the heats of formation of all the products, and then you subtract out the heats of formation of all the reactants. And of course, the heat of formation of O2 is 0, so this won't even show up in it. And you'll get minus 890.3 kilojoules, which tells us that this is an exothermic reaction, that this side of the equation has less energy in it. You can kind of think of it that way, as that side. So some energy must have been released. We could even put here, plus E for energy. Let me write plus some energy is going to be released. So that's why it's exothermic. But our question is this spontaneous? So to figure out if it's spontaneous, we also have to figure out our delta S. Our delta S. And to help figure out the delta S, I, ahead of time, looked up the standard molar entropies for each of these molecules. So for example, the standard, I'll write it here in a different color. The standard, and this is just a notation, the standard, no, there's no delta there. Let me erase, so I could just write it here. The standard, and standard, you put a little not symbol there. The standard molar entropy, so when we say standard, it's at 298 degrees Kelvin. Actually, I shouldn't say degrees Kelvin. It's at 298 Kelvin. You don't use the word degrees necessarily when you talk about Kelvin. So it's at 298 Kelvin, which is 25 degrees Celsius, so it's at room temperature. So that's why it's considered standard temperature. So the standard entropy of methane at room temperature is equal to this number right here, 186 joules per Kelvin molar. Not molar, per Kelvin mole. So if I have 1 mole of methane, I have 186 joules per Kelvin of entropy. If I have 2 moles, I multiply that by 2. If I have 3 moles, I have multiplied that by 3. So our total entropy is the entropy, or the total change in entropy of this reaction, is the total standard entropies of the products minus the total standard entropies of the reactants, just like what we did with enthalpy. So that's going to be equal to 213.6 plus, I have 2 moles of water here, so it's plus 2 times, let's just write 70 there, 69.9, almost 70, plus 2 times 70, and then I want to subtract out the entropy of the reaction, or this side of the reactants, or this side of the reaction. So the entropy of 1 mole of CH4 is 186 plus 2 times 205. 2 times 205. So just eyeballing already, this number is close to this number, but this number is much larger than this number. Liquid water has a much lower, this is liquid water's entropy. It has a much lower entropy than oxygen gas. And that makes sense because liquid form, there's a lot fewer states. It kind of takes the shape of it all falls to the bottom of the container as opposed to kind of taking the shape of the room and expanding. So a gas is naturally going to have much higher entropy than a liquid. So just eyeballing it, we can already see that our products are going to have a lower entropy than our reactants. So this is probably going to be a negative number, but let's confirm that. Let's confirm that. So I have 200, let me see, I have 200, 213.6 plus, well, plus 140, right? 2 times 70 plus 140 is equal to 353.6. So this is 353.6. And then from that, I'm going to subtract out. So 186 plus 2 times, let me see, plus 2 times 205 is equal to 596. So minus 596. And what is that equal to? So we put the minus 596 and then plus the 353, 53.6. And we have minus 242.4. So this is equal to minus 242.4 joules per Kelvin is our delta S minus 2. So we lose that much entropy. And those units might not make sense to you right now. And actually, these are a bit of arbitrary units. But you can just say, hey, this is getting more ordered. And it makes sense because we have a ton of gas. We have three separate molecules, one here and 2 molecules of water, of oxygen. And then we go to 3 molecules again. But the water is now liquid. So it makes sense to me that we lose entropy. There's fewer states that the liquid especially can take on. But let's figure out whether this reaction is spontaneous. So our delta G is equal to our delta H. We're releasing energy, so it's minus 890. I'll just get rid of the decimals. We don't have to be that precise. Minus our temperature. We're assuming that we're at room temperature at 298 degrees Kelvin. That's 28. I should just say 298 Kelvin. I should get in the habit of not saying degrees when I say Kelvin, which is 25 degrees Celsius, times our change in entropy. Now, this is going to be a minus. Now, you might say, okay, minus 242. You might want to put that there. But you have to be very, very, very careful. This right here is in kilojoules. This right here is in joules. So we want to write, if we want to write everything in kilojoules, since we already wrote that down, let's write this in kilojoules. So it's 0.242 kilojoules per Kelvin. So I could put a 0.242, let me get rid of this right there, kilojoules per Kelvin. And so now our Gibbs-free energy right here is going to be minus 890 kilojoules minus 209. So the minus and the minus, you get a plus. And that makes sense that the entropy term is going to make our Gibbs-free energy more positive, which, as we know, since we want to get this thing below 0, this is going to fight the spontaneity. But let's see if it can overwhelm the actual enthalpy, the exothermic nature of it. And it seems like it will, because you multiply a fraction times this, it's going to be a smaller number than that. But let's just figure it out. So divided by 1, 2, 3. That's our change in entropy times 298. That's our temperature, is minus 72. So this term becomes, and then we put a minus there, so it's plus 72.2. So this is the entropy term at standard temperature. It turns into that. And this is our enthalpy term. So we can already see that the enthalpy is a much more negative number than our positive term from our temperature times our change in entropy. So this term is going to win out. This term is going to win out. Even though we lose entropy in this reaction, it releases so much energy that it's going to be spontaneous. This is definitely less than 0. So this is going to be a spontaneous reaction. As you can see, these Gibbs-free energy problems, they're really not too difficult. You just really need to find these values. And to find these values, it'll either be given the delta H, but we know how to solve for the delta H. You just look up the heats of formations of all of the products, subtract out the reactants, and of course you weight by the coefficients. And then, to figure out the change in entropy, you do the same thing. You have to look up the standard molar entropies of the products, weight by the coefficients, subtract out the reactants, and then just substitute in here, and then you essentially have the Gibbs free energy, and in this case, it was negative. Now, you could imagine a situation where we're at a much higher temperature. Let's say we're at the surface of the sun or something, where all of a sudden, instead of a 298 here, if you had like a, I don't know, you had a 2000 or a 4000 there, then all of a sudden things become interesting. If you had if you could imagine, if you had a 40,000 Kelvin temperature here, then all of a sudden the entropy term, the loss of entropy, is going to matter a lot more. And so this term, this positive term, is going to outweigh this, and maybe it wouldn't be spontaneous at a very, 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 very high temperature. Another way to think about it, a reaction that generates heat, that lets out heat, doesn't matter. That the heat being released doesn't matter so much when there's already a lot of heat or kinetic energy in the environment. So if the temperature was high enough, this reaction would not be spontaneous, because maybe then the entropy term would win out. But anyway, I just wanted to do this calculation for you to show you that, there's nothing too abstract here. You can look up everything on the web and then figure out if something is going to be spontaneous.
All right. I hope that was helpful with the kind of the added context, that example of the sun and things like that. Felt like he could talk a little faster and better than I could walking through that. And it was already there in that context. So does that make sense? Any questions on that?
If
Yeah.
it's spontaneous, then why do we have methane that doesn't react when there's oxygen present?
Yeah. So there's, I think that this is a spontaneous reaction if you overcome some activation energy. I think there's still an activation energy required for some reactions, but under standard conditions, if you have a methane and air mixture and you provide some activation energy, then you would have a runaway reaction. There might also be conditions where it is truly spontaneous and there's no question. So I think that if we looked at the Gibbs free energy, and it's a good question, and I'm not maybe we should just do the numbers on this to test it. But I think that in this room, if we had the right ratio of methane and oxygen, then we would probably need an ignition source. So it's probably a higher temperature that's required, but as soon as we have some ignition, then it's releasing a lot of heat, then everything around it can also heat up and do the same. But there are some conditions where if we just had a higher temperature, that at that moment, it is completely spontaneous and it just goes, right? So we'll look at, in a moment, ice melting, right? So we can predict that based on the Gibbs free energy. It is a good question. And I feel like I should know the answer, so I'll try to know that for next time. But I do know that activation energy is one thing, and catalysts often serve to decrease that activation energy required. So a lot of catalysis is all about doing just that. Okay, so a couple examples. One would be carbon in diamonds, and sorry to disappoint here, but the diamond is forever thing is not actually true. On the scale of a lifetime, it's true enough. But it turns out that carbon, so diamond is just pure carbon. It's a carbon allotrope. And it slowly transforms to graphite. That's one reaction. It probably also, I believe it also very slowly oxidizes in the presence of the trace ozone that's in our atmosphere. So if you have carbon as a solid, so lots of carbons, plus ozone, you're going to get some compound that has CO, and I'm just going to say XY, at least at the very surface of it. And so over a long time period, you'll have carbon, the carbon in a diamond transforming chemically into a less ordered state, the graphite. It's still fairly ordered there. And at the edges, you're going to have some oxidation. The book's not mentioning, or I guess this is still the article. article's not mentioning this one, but I happen to know that's possible, just extraordinarily slow. So I think that if you were to measure the weight of a diamond and then let it sit at room temperature, standard conditions for 500 years, I don't remember the exact number, but it's probably on that order, or maybe 1,000 or so is the half-life. So you'd actually eventually be able to measure it again and say, oh, that's half the size it used to be. I don't think it's noticeable in the course of a human lifetime, so we can treat diamonds as forever. You know, I'm not going to disappoint you guys too much. But it's kind of an interesting thing. We have some dynamics there that, well, it can happen. It's just sometimes pretty slow. Okay, so let's do an example then, also from this article. So you can look there if you want to go in depth on it. So let's consider an example that looks at the effective temperature on the spontaneity of a process. The enthalpy of fusion and entropy of fusion for water have the following values. So the delta H, fusion is really, I guess, what they're saying about forming ice or therefore unforming ice, that process change. So the change in enthalpy is 6.01 kilojoules per mole for that reaction, or I guess moles reacting. And the change in entropy, delta S, is 22 joules per moles reacting. So the question is, what is delta G for the melting of ice at 20 Celsius? Okay, this is fairly simple. We don't even need the chemical potential stuff at this point. But hopefully it'll kind of be a good, just show yourself that you can do it. And I'll go stepwise with you. All right, so our reaction is this change of solid water to liquid water, temperature 20 Celsius. Conversion to get that to Kelvin is add 273. If you want to be precise, I think it's 273.15. So that puts us at 293 Kelvin. From there, we remember that our reaction, or the term here, Gibbs free energy, we can describe as delta H minus temperature times delta S. And so we can start putting in our numbers there, right? So that we were given a delta H value, 6.01 kilojoules per mole. minus the reaction, minus the T delta S. So we're going to have temperature, 293 Kelvin, times the delta S. And the delta S term was 22, but the units are joules. So we need to put that to kilojoules. And it has K at the bottom there as well. So the, that's just the units, right? So the units will cancel with the temperature units. So we need to divide that by 1,000 to get 0.022 kilojoules. The rest of the units cancel just fine. And we do that math, and we end up with negative 0.44 kilojoules per mole that is melting, right? So it's a negative value, and we could do the same exact thing and check what happens at negative 5 Celsius, right? Or 0 Celsius. And if we do that, we'd recognize that at 0, this is probably coming 0 Celsius, this reaction is probably reaching approximately 0 for delta G, right? We're kind of at equilibrium between melting and freezing, or should be. And a negative number should give us a positive delta G, meaning it would be likely to go backwards in this particular reaction to form a solid, right? So that's kind of the point of that. Okay, makes sense? Keeping it simple at this point. Okay, so back to chemical potential. Now that we kind of have a better feel, hopefully, of where all this goes, why it's relevant, I'm going to go back into it and revisit the potential energy analogy a bit. So I mentioned today, again, the thought of taking a ball in a skyscraper, right? So for chemical potential, this builds into the Gibbs free energy, but it's just one component of it, right? So coming back to that topic, we can make some descriptions like, okay, if we define, let's see, sea level as our base, then in a physical system, that would be the base. In a chemical system, our condition is 25 Celsius, 1 atmosphere. So let's imagine oxygen then, a pure gas oxygen. We can define then the standard potential for that according to a known value here. But then we can check, okay, well, what happens if we go from that sea level and raise it up some? In the chemical analogy, we can say, well, now, instead of pure gas, we have aqueous dissolved gas at 1 molal concentration. Now we have a condition where we have, under those aqueous conditions, a different value. This is actually still standard for aqueous, right? Because it's 1 molal, so 1 mole per kilogram, 1 mole of oxygen dissolved in 1 kilogram of water at standard conditions. That's our definition of the standard state under aqueous conditions, but we see that's different than pure gas. So it's kind of like a different starting level. If we go from, in this case, the sea level to the lobby of the Empire State Building, is their example. That's going to make a difference in the physical system, and likewise, when we change from a gas to an aqueous system, we are changing the value, but it's still kind of a baseline we could look at. Okay, so then from there, we could go up the elevator, so to speak. That would change the potential energy in a physical system, or we could say we have now X moles per kilogram. So we've changed how much we have. We could go up or we could go down to the basement or whatever. And now we're going to take that chemical potential and that standard plus RT ln of X. Right? Functionally, that's how we put it in, and that's what builds into our delta G equations. Okay, so we can describe that visually if we like to, where we're looking at the activity as it changes, and we can always decrease the activity. So that's one thing that's kind of interesting. We can, in this physical analogy, we could imagine digging deep enough where we can always go further deeper. Of course, the analogy is not perfect, but we can consider that, and it doesn't really matter exactly how we defined a standard state, but it's kind of a sealed compartment that you can stop at the elevator and say, oh, this is the one. This is our value where we're at a standard reference state. This is ground zero. You could actually dig the whole building down deeper into and have many, many floors down, whatever. It doesn't really matter. It's just that reference state. So that's kind of the point here. Okay, when we do think about activity in, there's an interesting phenomenon. This relates to the diamonds and relates to trying to get pure gold or trying to get very ultra pure chemical to use in your lab or something. You've probably seen purity ratings, and if you've done any purchasing for stuff, you might have seen, oh, we can get the 99% stuff or the 98% stuff, and that's pretty cheap. But when we try to get 99.9% or 99.99%, maybe it's getting real expensive. It's like, what's the deal here? Well, it actually has to do with activity and the chemical potential in dictating how can we separate a pure substance. So, a value of activity, A, for a given species I, we can always have an activity that makes this chemical potential negative. So if we stop and think a moment, our chemical potential is defined as some reference state plus RT natural log of activity, right? And since the natural log of A here, if we take A towards 0, this becomes a negative number, right? So let's say to write it as natural log of A equals X, that's like saying e to the x power equals a, right? So just thinking about what the natural log is meaning, we can say we can find a value of a. Did I say that right? I think so. We can find a value of a where x has to be very small. So this whole term goes very small and very negative, right? So if we take the natural log of 0.0000, many zeros, what is the result of that? Well, this is a very negative number, right? In this case, I have 19 decimal places there. So e to the what equals 10 to the minus 19 has to be a very negative number, right? E to the minus 100 or something, right? Whatever it is, it's going to be a very negative number. And so that's going to give us a very negative number here for the RT ln of A. So there's always a case where our activity is so small that the reaction proceeds forward. Now, if you think about the activity, we recall this is a function of the activity coefficient times the substance of, we'll call it I, the concentration of it. That means if we have a very, very small concentration of it, we have a very small activity. So when we try to get something very, very pure, we are trying to get a very, very small concentration of something, right? And so as soon as we do that, we have a very low activity number and therefore a very small or very negative number here, which means we can potentially have a very negative number here when we put it all in the quotient, and therefore that eventually will make delta G naught minus that a negative net number. Then we get the reaction happening and it's hard to pull the stuff away, basically. That's the deal. So it's what we find is it's kind of, you know, thermodynamically impossible to have completely pure substances in that sense. We can get very close, at least close enough for our relevant things. Some substances like gold, we call it noble for a reason. It stands apart. It doesn't like to react with any of the lesser elements or whatever. It's pretty conducive to that, but it's still not 100%. And our book goes through an example of silver with gold. Okay. So we only have 10 minutes left. I think I'm just going to leave off here and work with this with you next time. Like I said, that might be tomorrow, or not tomorrow. Definitely not tomorrow. Might be Thursday if all goes well. And welcome you to join, but completely understand if not. You don't even have to tell me. If you have a situation where you can't attend and you're in a bad spot, probably can't do anything until next week sometime, feel free to drop me a line when you get a chance, but no pressure. I understand. And this is going to be, if I do lecture, it'll be posted, so you'll have it. So take care and be safe.